Hi folks, welcome back. Section 10.7 here, trig equations and inequalities. I've mentioned this several times. We've got 12 example problems to watch and work through here. It's going to take us a while. We're going to continue marching on through. Every one of these examples is important for a reason. I didn't pick these at random. These all have something to do with problems you might see in the future, so please don't get bogged down in watching these videos. Make sure you get through them all because you're going to see things that will help you out in the future. All right, so we've already seen quite a few of these. Kind of flipping through. There was example 5. Our good friend JB helped us through that one. Now we're going to move into something new here. We're going to start looking at equations with more than one trig function inside of them. And we're going to get started by reviewing a couple things. First thing, let's talk about this. Do you remember the trig identity hidden in this figure? I hope you do, because we're going to see it again. And that trig identity involved the Pythagorean theorem, but not just with cosine squared plus sine squared equals 1. That one's pretty straightforward. The one that we saw that was a little more obscure than that was this leg squared plus this leg squared equals the hypotenuse squared. And I'm going to go ahead and relabel these sides for you because you're going to see this one again very shortly. This side length here is 1. This side length here is tangent of theta. And the hypotenuse, this entire length here, is secant of theta. Whoa, you deserve better than that, folks. Secant of theta. So the trig identity here is as follows. Tan squared of theta plus 1 equals secant squared of theta. And that is another of the Pythagorean trig identities. All right, so let's now look over here at this seemingly simple equation I'm asking you to solve. X cubed equals x squared. So I'd like you to solve that, and I know this is what you're going to do. You're going to do this. You're going to say, oh yeah, Mr. S, I'm just going to divide by x squared on both sides. And over here, that gives me 1. And then over here, let's see, x cubed divided by x squared. I'm going to subtract the exponents. That gives me x. So x equals 1. I'm done. I get to go home. That was easy. I have no homework tonight. Unfortunately, you committed a fatal error. So I am going to bring out my friend the pull tab to show us what that fatal error is. Don't ever divide by something that could be 0. It's downright dangerous. We divided by x squared here in this equation. What if x squared is 0? We divided by 0, and that's completely illegal. So how should you approach this problem? Well, we can't divide by something that could be 0, so we're going to have to resort to something else. Let's try subtracting x squared from both sides. When I subtract x squared from both sides, I get x cubed minus x squared equals 0. Doesn't look like it really helped us, but I do remember something from the past. Anytime I have an equation with a 0 on one side, it kind of makes things easier to solve. From this point, I'm going to go ahead and try to factor out a GCF. And I think I got a GCF here of x squared. And that's going to leave me with a remaining factor of x minus 1. So now I have x squared times the quantity x minus 1 equals 0. And from this, we can really do some damage. If you remember, this is a product. And I hope you remember something called ZPP, the zero product property. Anytime we have a product that equals 0, it means that either factor can be 0 as a solution. So that means x minus 1 equals 0 or x equals 1. Hey, we've already seen that solution, but here's the one we didn't see. Our other factor is x squared. So if x squared equals 0, that means x equals 0. So we did, in fact, in the previous attempt, we did divide by something that was equal to 0, and that's a problem. We lost visibility to this solution when we divided both sides by x squared. So I'm going to discourage you from dividing by anything that could be 0. think about subtracting it, factoring, and then solving whatever other equations come out from the zero product property. Folks, I have one other warning here for you. Let me see what we got on this pull tab. In addition to don't divide by something that could be zero because it's dangerous, please also remember to do this. All right, folks, I got one other warning for you here before we move on to a new example problem over here in this other pull tab. So in addition, remember, don't divide by something that could be zero because it's dangerous. Also, don't run with scissors because that's dangerous too. Now that we have that out of the way, let's move on to our next example problem. All right, so here we go with question 6. Solve the following equation, giving exact solutions which are on the interval from 0 to less than 2 pi. So slightly different instructions than the previous problems we've been solving. This one, we only have to give the solutions on the interval from 0 to 2 pi. And one thing I'd like to do is kind of, I showed a couple students this the other day, and I think it was helpful to them. So if I draw a number line, and I mark something on it, like if I mark 0 right here, and I mark 2 pi right here, all my solutions have to fall in the interval such that 0 is okay, because I'll show that as a closed circle. 2 pi is not okay, and then I have to be between those values. So if I'm going to shade this number line, all my solutions have to be in there. So if you come up with a solution that is negative, it's not correct. It's got to fall on this interval. And if you come up with a solution that's, let's say you come up with a solution that's 7. Is that number a valid solution? Well, the answer is no, it doesn't fall on this interval because 2 pi as a decimal is approximately 6.28. So use this as kind of a guide to figure out if you're on the right track or not. But let's get going here with number 6. I have an equation that says sine of 2x equals sine of x. First thing that jumps off the page at me is I have a double angle here, so I'm going to use the double angle formula for sine. That'll be 2 sine x times cosine x, and that still equals sine x. And the next thing you're going to be tempted to do is divide both sides by sine x, and then you're going to get 2 cosine x equals 1. And at that point, I'd say you've committed a potential algebra felony. You divided by something that could be 0, and we're not allowed to do that. So we have to have another strategy. Let's subtract sine x from both sides. So if I subtract sine x from both sides, and I'll just write it out here for you, minus sine x minus sine x. What we end up with is an equation that looks like this. I have 2 sine x cosine x minus sine x equals 0. So we have a 0 on one side. That's good. That anytime we're trying to solve an equation, we want to have a 0 on one side because it makes we have more tools for this situation. And what I see right away is that I got a sine x and a sine x. So I can factor out sine x. And I'm left with my other factor of 2 cosine x minus 1, all equals 0. So again, I hope this is jumping off the page at you right now. What we have here is a product, sine x times this other factor, that equals 0. And anytime we have a product that equals 0, we should be thinking zero product property. So if this factor is 0, then we have a solution. If this factor is 0, we have another solution. Let's go ahead and take a look first at this factor right here. So if I have 2 cosine of x minus 1 equals 0, I can solve for cosine of x. That'll be cosine of x. If I add 1 to both sides and divide by 2, I have cosine of x equals 1/2. All right, and then now I have to think about my unit circle. Okay, cosine of x equals 1/2 when x equals pi over 3 or 5 pi over 3. So that's a value in quadrant 1 or quadrant 4. And again, does that match our interval? It sure does. It falls on that interval for allowable solutions. So there's one set of answers. Now we have to consider when sine of x equals 0. Sine of x equals 0, well, let's see, sine is the y coordinate, so that equals 0 at an angle of 0 radians and pi radians. Bingo. There's our there's our two sets of answers. If we were to list these kind of in a comma-separated list, which is probably what WebAssign will ask you to do, you're going to do something like this: x equals 0, comma, pi over 3, comma, pi, comma, 5 pi over 3. I chose to list those in increasing order. That's up to you whether or not you do the same thing. And that's it for example 6. Let's go ahead and move on to example 7 now. Okay, example 7 here, we have equation secant squared of x equals tan x plus 3. We need to have the same instructions as our previous example. So we need to find all the solutions which lie on the interval from 0 to less than 2 pi. So anything, folks, you deserve a better 0 than that. Anything from 0 to 2 pi, not including 2 pi, but including 0. So anything on that interval is an acceptable solution. So right away, this might scare some of you, this example problem, because we got secant flying around and there's a tangent in there, and then that seemingly random number 3. But this one isn't too bad if you think back to our Pythagorean trig identities. Secant squared of x really is equal to 1 plus tan squared of x. And that is going to equal tan of x plus 3. Well, some of you still don't really have any idea what to do at this point, and that's okay, but pay attention to a little algebraic magic here as I rearrange this equation. I'm going to write it as tan squared of x minus tan of x minus 2 equals 0. So what I did is I subtracted tan x from both sides, and I subtracted 3 from both sides. 1 minus 3 is negative 2. Still, some of you are bothered by this. This is like you're wondering, where the heck's he going with this? But does this equation here look anything like this one? U squared minus u minus 2 equals 0. Can you see any similarity there? And if I have an equation u squared minus u minus 2 equals 0, could I factor that? Could I say that's really u minus 2 times the quantity u minus 1, excuse me, u plus 1. Oh, we got a bad print. That was a morphed number 1 in parentheses at the same time. Okay, so can I factor u squared minus u minus 2 equals 0 into the quantity u minus 2 times the quantity u plus 1? You bet we can, because we learned how to factor in algebra, so we can still do that. This is now an easy problem to solve. Okay, I have a product here. I have this product times this product, or this factor times this factor, so it's a product, and it equals 0. So that means u plus 1 equals 0, or u equals negative 1. And if I look at this factor, I have u minus 2 equals 0, which tells me that u equals 2. So what I've done here is a form of u substitution. I've looked at a similar equation and said, I know what the solutions are to u squared minus u minus 2 equals 0. Can I transfer that knowledge over here? Well, I sure can, because what I'm going to do here is I'm going to say that u equals tan of x, and that is the connecting piece between these two strategies right here. Okay, so now what I have to say is tan of x equals negative 1, or tan of x equals 2. Now, so we have two equations to solve. This one, really easy to solve. This one, not so easy. So I'll do the easy one first. So we have tan of x equals negative 1. Where is the tangent ratio negative? Well, tangent ratio is negative in quadrant 2 and quadrant 4. I know that tan of x equals -1 at x equals 3 pi over 4 or 7 pi over 4. Check your unit circle, folks. You'll see that at each of those angles, the x and y coordinates are the same, except one of them is negative and one is positive. So here's one solution to this equation. Now I have to deal with this other one here, tan of x equals 2. This one's a little bit trickier, a little more abstract. Some of you are going to be bothered by this, but please persevere through this challenging problem. So if tan of x equals 2, and there is no angle on our unit circle that has a tangent ratio of 2. But what I can say, I can say this: x equals the tangent inverse of 2. Okay, so x equals tan inverse of 2. Well, what does that mean? That is an angle in quadrant 1. Okay, so that's an angle in quadrant 1. I know that the angle measures in quadrant 1 are okay because they fall in this interval. So I have tan of x, x equals tan inverse of 2. Just for fun, you should convert that to a decimal and make sure that you see. This is, by the way, this is an exact answer. Exact answer. You want to see the decimal, you're going to need to plug that into your calculator. Okay, so am I done? I don't know. I'm not sure if I'm done yet. So what I'm really going to do is I'm going to go ahead and graph these two things, secant squared and then tan x plus 3. I'm going to graph each of those, and we'll take a look at the graphs. All right, so let's graph each side of this original equation as a function. We'll graph y equals secant squared of x and y equals tan x plus 3 and see where they overlap. I've already set up the x and y axis, so I'm looking here from 0 to 2 pi on my x-axis, and then I've picked one on the y-axis that I know is going to work. So I'm going from 0 to 10 here. So let's go ahead and graph secant squared. So we got secant x, and we want to square that. So there's the graph of secant x squared. Now I got to do tan x plus 3. So I'm going to graph tan x plus 3. Okay, so there we have our solution, and let's go ahead and take a look at this. We have one point of intersection there, a second, a third, and a fourth. We should have 4 solutions when I look at this interval. Let's go back and take a look at what we have on our paper. Well, I got 2 solutions here. So let me number these here. We got 1, 2, 3. Uh-oh. We only have 3 solutions. What on earth are we missing? Well, remember that tan of x equals 2, or x equals tan inverse of 2, that's an angle in quadrant 1. There is also an angle in quadrant 3 who has a tangent ratio of 2. In order to find that angle, I need to add pi radians to my previous answer. So pi plus tan inverse of 2 is my x value in quadrant 3. And now I have a complete solution set. So let's go ahead and write all of those out. I have x, and I'll write them in order of increasing order. It's going to look kind of crazy. So I have x equals tan inverse of 2. 3 pi over 4, pi plus tan inverse of 2, and then 7 pi over 4. Okay, that's my final answer. And just to kind of make a connection here between some of these exact answers and approximate answers, let's look at the decimal value here for this one. I'm going to look at pi plus tan inverse of 2. So I'm going to go back to the calculator page, and let me go ahead and add a page here, calculator page. Let's do pi plus inverse tangent of 2. And I want a decimal answer, and notice I'm in radians here, so my output's going to be a radian value. So a decimal answer, I'm going to force it to be a decimal by adding a decimal point there, grip it and rip it, and we get an answer of 4.2487. And that was the third solution I listed when I listed them in increasing order. So let's see if I can find this number on my graph anywhere. So going back to my calculator page, this is the first, second, third intersection. So I think this one here should be that 4.2 number. What I'm going to do is ask my calculator to find that point of intersection. Oh, there it is. That's that 4.2 number. Okay, matches what we saw over here. 4.248 rounds to 4.25. Okay, so again, what am I doing there? I'm just trying to make a connection between these very abstract looking answers and decimals, which some of us are way more familiar with and more comfortable with. All right, folks, this is a long video. Again, apologize for the length, but a lot of important stuff to talk about here. So that's examples 6 and 7. Remember, we're going all the way up to example 12, so persevere through these long videos.